Все началось, да?
Да.
Хорошо.
Заметьте в петличке батарейки, потому что...
Нет, там полный заряд, я проверил.
Да, проверил?
Да,
Ну, хорошо.
вторая просьба у меня была, камера как-то криво стоит, нельзя ли ее как-то выровнять? Сейчас, ну тогда я буду начинать. Введение в коммутативную алгебру.
Да, мы это делаем, да.
Okay, so today we're going to continue elements of homological algebra, exact sequences, and today we're going to finish this little topic. So there will be 2 more statements without proof. So the next statement is the well-known 5 lemma. And this is the following statement. So suppose you have 2 sequences of modules, and the length of each sequence is exactly 5. So you have M1, M2, M3, M4, and M5. So let's call maps in the first sequence alphas. So we have 4 maps. And we have another sequence, again, with 5 modules. So let's call them N1, N2, N3. And the maps between them I'm going to call beta. So, and suppose that we have a map between these 2 exact sequences. So it means that we have a maps between all modules and of course, to say that this is a map between 2 sequences, we need to say that all the squares that we see here are commutative squares. So all squares are commutative. Or commuting. I guess this is the same thing. Okay, so we have this diagram, and if you want to formulate this 5 lemma accurately, you need to say the following. So suppose several things. Suppose that the maps F2 and F4 are bijective. So this is the first assumption. The second assumption is that F1 is surjective. And the last assumption is that F3 is no. I have also assumptions about F5. So assumptions about F5 is that this is injective. Yeah, so F2, F4, F1, F5. So if you have these 3, then the conclusion is that F3 is an isomorphism. So this will be a statement without proof, but sometimes it is useful, so maybe we will use it to solve some problems on seminars, and maybe we'll use it later to prove something about commutative rings. You can find proof essentially in any homological algebra textbook somewhere in the beginning.
Is it the same as saying that F2 and F4 are isomorphisms, or?
Yeah, so you can as well say this is isomorphism, this is surjective, and map of modules, you can say this is epimorphism, and this is monomorphism. That's just another language to say the same thing. Okay, next statement actually I think is quite interesting, and I'm going to prove this, but perhaps you also see the proof of this statement in your homological algebra course if you take it. So the sequence of modules, so such sequences are called exact on the right. So we have M prime is mapped to the M, this is mapped to the M double prime, and I have 0 on the right. So the sequence is exact. So maybe let's give a name to the maps. So let's call the first map alpha and the second map beta. And so the sequence is exact. What it means? It means by definition that the image of alpha is the same as the kernel of beta. So that's the exactness of this term. And also we need to say that the beta is a surjective map. So this will be exactly the exactness of this term. And at this term we have only one arrow, so we cannot even impose any conditions. So there are no conditions here. Okay, so this sequence is exact if and only if the corresponding sequence of homes is exact. So the sequence is the following. You have 0. This is mapped to the home m double prime n, and then this is mapped to the home m n, and finally, so unfortunately I'm writing the statement on the small whiteboard. So the last home is between m prime and n. So if and only if this sequence is exact for any module n. So first of all, of course, the first observation is that this exact sequence gives us a sequence, maybe not necessarily exact, but at least we have a sequence, we have maps here between homes, right? And maybe I need to kind of illustrate this before we do the proof. So let me take the sequence that is given to me. And I have an element. So by the way, have you seen this notation home? This is just the, well, you can say this is a set of all module maps between these two modules, but of course this is not just a set, this is again an R module, because this is commutative ring. Notice that this won't be true over a non-commutative ring, because if you have a non-commutative ring, you, for example, take two left modules, this is just an abelian group. But for a commutative ring, this is again an R module over the same ring R. Okay, but I want to show you why there is, for example, a map like this. Well, suppose I have a homomorphism, module homomorphism from m double prime to n, so I can write it like this on the diagrams. Let's call this phi. But then, so I call this map beta. So then I can take just the composition. I take this composition, so if phi lives in the home, and sometimes actually people to indicate that you work over a fixed ring R, people write home over R, but in our case the ring is understood, it is fixed, so this is essentially the same notation. So phi is in the home m double prime n. So then if you take the composition, you kind of precompose phi with the beta, you'll get an element in the home m n, right? You can just see this from the diagram. So this is our map. This is the first map here. And because this is kind of induced with the precomposition with beta, I'm going to call this map beta bar. And for the same thing, for the second map, you do exactly the same thing. Suppose you have now some map. Say if you have some map, let me draw this on the same diagram. You have some map, say psi. This is a map to the n, so it's something that lives here, right? So this is the map. You can precompose this with alpha, and this gives you a map between m prime and n. So this whole composition will be an element here. So again, this map here is just the precomposition with the given map alpha. So these two maps between homes are induced by the maps alpha and beta. Okay, any questions about the definition of these two maps? Okay, if this is understood, we understand that we have at least 3 homes and 2 maps between those homes. We need to show that one exactness is equivalent to another exactness. So, proof. So we need to go into 2 directions. So let me start with the direction where I assume that this sequence is exact. So so now then for any map, let's call this map phi. This is a map from the m to the n, such that the composition of this map phi with the alpha is 0, well, for any such map, so I want to show, I need to show I assume the exactness of the first sequence, I need to show the exactness of the second sequence. So I take some element phi in the middle, so I want to assume that this phi, if I apply, so this condition is exactly the same condition that if I apply alpha bar to the phi, I'll get 0. So I take a map, and I suppose that this map is in the kernel of the map alpha bar. So I want to show that it's actually in the image of the beta bar. Well, there is map psi, which is a map from the M double bar. And I know, so I want to construct a map somewhere here. So I know that the M double bar, I can as well just say that this is, quotient of the M by the image of the map alpha, right? So this follows immediately by the exactness of the given sequence. Okay, so there is a map psi from
beta, image of beta, like M double prime is...
No, it's image of alpha. So this beta is surjective. It means that the image of beta, which is exactly M double prime, is the quotient of M by the kernel of beta, and the kernel of beta is exactly the image of alpha. So suppose there is a map psi from this M double prime, which we understood as M quotient by the image of alpha, to some, there is a map psi from M double prime to the N. So what's the definition of this map psi? Well, I can just say that by definition, if element on which I want to define this psi is just a class, right? So I can take a representative of this class, say I take M plus the image of alpha. And what would be this map psi? Well, this will be exactly phi applied to M. Right? So let's define psi by this formula. Well, first of all, we need to check this is a well-defined map, but this is immediately clear because if you choose another representative, because the composition of the phi and alpha is 0, the answer will be the same. So the map is well-defined. It doesn't depend on this choice of M. And that's exactly what we want, right? Because we now see that if I start with any map that lives in the home between M and N, I can construct another map. And well, if I just precompose this map with the beta, I'll get exactly the map that I started with. Okay, so what we've done, I think we've checked the exactness at this term. So we now also need to check the exactness at the very first term. But the exactness at the first term is more or less automatic, or because if you just look at the original diagram, so maybe let's go to the original exact sequence. Right? Now suppose I have a map M double prime to N, so the map like this. And I want to check that I have the embedding at this term, so beta bar is embedding this home to the home between M and N. So it means that I want to show that if I precompose with beta and I'll get 0, then actually the map is 0. But this beta is surjective. So that's the end of the proof. If you take a composition of surjective map, some map, and if you know that this composition is 0, this is only possible if the given map is 0, since the beta is surjective. So we have an exactness at these two terms, and that's exactly what we need to finish the proof in one direction. Now let's go in the other direction. So now I assume that I have exactness of the second sequence with the homes, and I want to derive the exactness of the first sequence without homes. Well, I need to check several things. So first, of kind of 3 steps. So the first step is to show that beta is surjective. Well, if beta is not surjective, well, it means that I can consider a map from the m double prime to the m double prime quotient by the image of beta. If beta is not surjective, then this map is not 0. Is not a 0 map. But its composition with beta is 0. Right? Just by definition of this map, because if you precompose this with beta, everything that is in the image of the beta under this map is mapped to the 0. So beta has to be surjective, right? This map has to be surjective, because we see if this is not surjective, well, the idea to, when we prove in the other direction, in this direction, so the idea is always to kind of plug in some specific modules instead of n. So the statement is true for any n, so we want to try different n's. So in this case, you can think about this quotient as the n that we want to use, and we want to look at this exact sequence of Holmes with that particular n. So we see that with that particular n, we'll have an element, we'll construct it, well, if beta is not surjective, we get an element here, which is not a 0 element, right? But the composition with the beta gives you a 0. So that's immediately a contradiction with the exactness at this term of the Holmes. Okay, so this finishes the first step. Now the second step is the following. I want to check that the composition of the beta and alpha is equal to 0. So I have the exactness of the Holmes. I want to check at least that composition of these two maps in the given diagram is 0. Well, this follows more or less immediately if I choose n to be the m double prime. Now, in this case, if I choose n to be m double prime, I have the identity map here. So here in the Home, I have a canonical map, which is just the identity. And I want to apply the beta to this identity, and then I want to, beta bar to this identity, and then alpha bar to this identity. Well, because I know that this sequence is exact, if I apply first map and then apply the second map, I'll get 0. So it means that if I take the identity on the m double bar, then I apply beta bar, then I apply alpha bar to this, I'll get 0. Oh, maybe composition. What I do when I apply beta bar, I just precompose with beta. So this thing is exactly beta. And when I apply alpha bar, this is exactly the precomposition with alpha. So this is beta, but this whole thing, this is exactly the composition of beta and alpha. Right? So the composition of beta and alpha now is equal to 0. Okay. So if the composition of the beta and alpha is 0, at least we can say that the image of the alpha is contained in the kernel of beta, which immediately follows from the last observation that the composition is 0. So what we need to do, we need to show that there is inclusion in the other direction. So this is step 3, I guess. Yeah, so this is step 3. So in the step 3, I want to show that the image of alpha is exactly the kernel of beta. Again, to do this, I need to choose particular module. So I choose m to be the quotient of the m by the image of alpha. and I want to take map phi from the m to the n to be the canonical projection, or canonical surjection on the quotient of is the canonical surjection. Okay, now clearly if I apply alpha bar to the phi, I'll get 0. Again, this follows immediately from the definition of the n and this map phi. If you precompose this and then you take a map that maps everything in the image of precomposed with alpha and take a map that sends image of alpha to 0, you get this as a 0 map. Now, because I have the exactness of the Holmes and phi is such an element that alpha bar of this element is 0, it is actually, well, beta bar of something. So by exactness, there is another map psi from the m double prime to the n, such that phi, well, I can write phi is equal to the beta bar applied to this psi, but I can as well write this as a composition of psi and beta. Okay, now let's look at this identity. This identity is telling us that the kernel of beta is contained in the kernel of the map phi, right? Because it's just this composition. If something is, I apply beta and get 0, and phi this composition, I apply this to the same element because I get 0 here, it's clearly in the kernel of phi. Now, what we can say about the kernel of phi? Well, that was the canonical projection to the quotient by the image of alpha. So, more or less by the definition of this map, it follows that the kernel is exactly the image of alpha. But look, that's what we actually wanted to prove, right? We have inclusion on the previous step in one direction, and now we prove the inclusion in the other direction. So that's the end of the proof. Okay.
I'm sorry, could you repeat the final steps in the first direction?
This step?
Yeah.
Well, we in this proof we need to do the following. We need to check the exactness at the two terms. We check the exactness at this term, and then we check that there is exactness here. So to do this, suppose you have a map. So here I guess I can say that there is a phi, and this is this phi. So this is map that lives here. And now you know that when you apply beta bar to this map, you get 0. You want to show that this is that this map, this beta bar, is an inclusion. So this is a monomorphism. So, well, this is a monomorphism of the two modules. So you take an element, you apply beta bar, you get 0. You want to show that this element phi is actually 0. If you can do this, this is the exactness at this term. That this map is injective. Well, this is the map. So this composition is the beta bar applied to the phi, right? You know that this composition is a 0 map, and you also know that this map is surjective. So I guess you can prove from this that this means that this map is actually 0. We can do this on the level of the elements, for example, right? You take some element x here, you want to show that f on this element is 0, right? But this x is the image of some y, right? But on this y, you know that when you apply this composition, that on the y you get 0. So there is no choice that phi on this x is actually equal to 0. Okay, so by the way, notice, maybe I haven't mentioned this, but this is an important remark. If you look kind of at the construction, when you apply home and you fix the second argument, that's exactly what we do in this proposition. We fix the second argument, this is some fixed module n, and then we apply this to an exact sequence. we get an exact sequence and kind of go in the other direction, right? So you finish here with M double prime, but here you start with M double prime. So sometimes when you do homological algebra or some category theory, people say that in the first argument, this functor is contravariant. It inverses the directions of the maps. If you go like this, then when you apply home, you go in the other direction. But in the first argument, if you do home like this, so I fix the first argument and apply say home to this exact sequence, you still get an exact sequence of the kind of the same type. You don't reverse the direction of arrows. And this will be next proposition. You can prove this next proposition essentially by the same arguments. So I'm not going to give you the proof. This will be an exercise. Maybe we will do this on the seminar if we have time, but I guess probably we won't have time to prove this. So next proposition, which is dual version of this proposition, the sequence with the 0, M prime, M and M double prime. So notice that it's kind of dual situation. I have 0 on the left, but not on the right. So it's exact only on the left. So this sequence is exact if and only if the sequence of homes, so now I have more space, and the sequence of homes is almost the same, but now I fix the first argument, and this is some module n. So the sequence is exact for any module n. So the proof is exercise. Yeah, so notice that now we have 0 on the left. It's the same 0 for the homes. It is kind of the opposite situation from the previous proposition where we have to switch 0 from the right to the left. And also here, for example, if I give the same names alpha and beta, these maps between homes are again induced by these alphas and betas. Well, for example, if you have a map, say, phi, right? So this is a map from n to the m prime. So it lives somewhere here. You can again now post-compose with alpha, and then you get this map from n to the m. But this map lives exactly here. So now the map that we have here between homes is post-composition with the alpha. And this map is again the post-composition with the map beta. So this is how you get this map between homes. But I'm not going to give you the proof that it's exact. So I guess the ideas that we have in the previous proof is enough to prove this statement. Okay. So next we have a important but kind of straightforward definition. So definition, short exact sequence. Well, for shortness, people not to write this short exact sequence all the time. People use SES, short exact sequence. So recall that the short exact sequence is the sequence of 3 modules, well, and zeros on the left and on the right, and have exactness at all 3 terms. So this short exact sequence splits. So this is definition of the word splits for a short exact sequence. If there is an isomorphism, so there is an isomorphism, let's call this isomorphism phi, between module m and the direct sum of the m and m double prime, such that we have several conditions, and to write these conditions I need names for these maps between in the exact sequence. So let's call this alpha and beta. So such that composition of the phi and alpha is the same thing as the canonical embedding of the m prime into the direct sum, and the composition, so the beta is the composition of the canonical projection on the m double prime with the map phi. So in a second I'm going to write this as a commutative diagram. It will be much easier to remember and understand these two conditions. So perhaps it's better to write in terms of diagrams. So we have short exact sequence. And you have kind of the easiest possible short exact sequence that you can imagine. This is just m prime is embedded into the direct sum, and then there is a projection on the second factor of this direct sum. So this is pi m double prime. And the fact the short exact sequence splits means that there is an isomorphism between these two exact sequences. And an isomorphism, as we agreed, has to be a map such that all the squares are commutative. But here, these two maps, this is just the identity map, and the commutativity of these two squares are exactly these two conditions. If I don't have mistakes here, of course. So let's check this alpha, beta. So I see that if I take the composition of alpha and phi, well, this is just this. Because this is just the identity, it's not really a square, this is kind of like a triangle. So this composition is the iota m prime, and the composition of the phi and the projection. Yeah, so the composition of the phi and the projection is exactly beta. Yeah, so it looks like these two conditions are correct. Okay, so proposition. So I think this is a relatively important statement, so we're probably going to prove this on the seminar, but not on the lecture. So the following are equivalent. So the first condition, that the sequence splits. In the sense of this definition. So it means that there is this map phi and all these squares are commutative. So the second condition is that there is a retraction rho. So this is a map m to the m prime such that the composition of the rho and alpha is the identity on the m prime, also on the m prime. So it means that if you go back to the short exact sequence, so this is map alpha, and there is a map rho that goes in the other direction, such that the composition, if you first apply alpha, then you apply rho, you go from m prime to the m prime. By this composition, this has to be the identity on the m prime. So the word retraction exactly means that you have a map that goes on the other. Oh, suppose you have an injective map. The retraction of this injective map is exactly the map that goes in the other direction, such that the composition is the identity. So that's the definition of retraction. So this is the second property, and of course the third property is dual. For this surjective map, you have the section. So there is a section. Let's call this section sigma. So now this will be a map from the m double prime to the m, and of course if you take the composition of the, so the second map is beta, of the beta with the sigma, you'll get the identity map on the m double prime. Okay, maybe I just write this section also on the diagram. So now the section is here. So this is the map sigma. So if you apply sigma, then apply beta, you will get a map from m double prime to m double prime, and this has to be the identity. So these three conditions are equivalent. Of course, you can see that there is a symmetry between the existence of the retraction is the same as the existence of section. Maybe it's a little bit surprising. Well, I hope this is surprising if you haven't seen this before. But also, this is kind of practical way to show that the short exact sequence splits, because in fact, it's much easier to find a retraction or a section than to check that there is an isomorphism between these two things and then check the commutativity of the two squares. This is the retraction.
And also, I wish to ask, can we apply 5 lemma to these two sequences on the left?
Well, to apply 5 lemma, you need to know that there is a map like this. If you know, for example, conditions 2 or 3, you need to use them to construct a map, and then to check that this map is an isomorphism. In the conditions 2 or 3, there is no map phi.
But I mean that identity map isomorphism between m strip and m strip and m to strip and to strip, and we can set two maps from 0 to 0, which also isomorphisms.
And what will we get? I don't quite understand what.
I mean, it seems that conditions of 5 lemma satisfied. If we add.
No, but just tell me what you're trying to achieve. What's the goal of what you're saying?
I just don't understand. It seems that we can apply this lemma, but it's not always the case that's why isomorphism.
Oh,
If we have
Yes, if we know that this commutative diagram, then phi is isomorphism by 5 lemma.
yeah, that's true. Yes.
I mean, if we add two maps from zeros on the right and left, and we
Yeah.
get exactly, yeah. And according to this lemma,
Yeah, but this should commute.
Yeah, we need to have commutative squares everywhere. So commutativity here is trivial, but here we still have these conditions. Okay. So next section, projective modules. Again, projective module is something that you usually study in homological algebra to construct something like projective resolutions and then use them to define and compute derived functors. But in commutative algebra, it's also very convenient and useful class of modules. So I want to prove at least very basic things about projective modules. So first definition, a module P is called projective if for any surjective map of modules, of course, beta m to n and any map f p to n, there is map sigma p to m such that the composition of the beta and sigma is equal to the map f. So again, it's much easier to remember and present everything in terms of the diagrams. So this surjective map I can draw as following. I have a diagram like this. So the surjectivity means exactly that I can add this 0 on the right. Now I have some map f to the n. And the claim is that it kind of can lift this map F along the map beta. So there is a map lifting F. So there is a map.
Yes, there should be
It's
phi.
between n and n.
Huh?
Not n, but p.
Yeah, thank you. So this is of course P. Yeah. So F is a given map. Then there exists a lift of this map. This is the map sigma. And this last condition is exactly the condition that this triangle is commutative. If I apply sigma, then I apply beta, I'll get exactly F. So I think it's easier to remember this. So you start with any surjective map, then you can lift any map from a projective module along this surjection. Okay, so proposition. There are several ways to characterize projective modules. Well, we can of course use the definition. So again, the following are equivalent. So the first condition is that P is projective in the sense of this definition. Now the second condition is that any short exact sequence of the form you have 0, some module k, some module m, and at the end you have projective module. So this splits. When you have p in the beginning, well, that kind of depends on how you look at this thing, but if you have p in the short exact sequence on the right, you can say that any such short exact sequence splits. So condition number 3 is that there is module k such that if you take a direct sum of k plus a given projective module p, then this is a free module. So condition 4, any exact sequence, well, any short exact sequence as before, 0, m prime, m double prime, induces a short exact sequence of Holmes. So we have 0, home, p, m prime, home, p, m, and home, p, m double prime, and then again 0. So in this sense, it means that when you remember, part of this definition is correct. So if you forget the 0 on the right, you can always say that there is a exactness like this for any module p without the exactness here, without the 0. But for a projective module, this is the nicest possible situation. Short exact sequences by the home with a fixed first argument are mapped to the short exact sequences. So this is condition 4. And the last condition the last condition is 5. Any monomorphism, so for any monomorphism beta m to the n induces not monomorphism, epimorphism.
Is it like any exact short exact sequence a tautology?
Yeah, I just wanted to write short exact sequence, and so any short exact sequence like this induces a short exact sequence of Holmes. Now, last condition, that any epimorphism between modules m and n induces an epimorphism of the Holmes. Okay, so let's prove this. So I guess, well, we're going to prove that these 5 conditions equivalent by going in a circle from 1 to 2, 2 to 3, etc., 5 to 1. So some of the implications are, of course, more or less trivial. So let's try to go from 1 to 2. So what we know. So we have the definition of projective module, and we want to show that any short exact sequence splits. So let's take a short exact sequence with modules k, m, p. And what I want to do, I want to take this projective module p again, and have a canonical map from the p to the p, which is just the identity. Right? I can always do this. Now, because this map is surjective, module p is projective module, there is a lift. Let's call this lift sigma. But since this is just the identity map, this map sigma is exactly this section. And this finishes the proof from 1 to 2. Because we just apply this condition 3 of the previous proposition. Okay, now let's go from 2 to 3. So 2 tells us that any such short exact sequence splits. We need to show that all projective modules are direct summons of free modules. Okay. So how we can do this? Well, let S be a set of generators of the projective module P. Well, if I have a set of generators, I have a surjective map. Of this form, right? Because here this is just direct sum of as many copies as I have elements in the set S, and what you just do, you just kind of take the standard basis here and send this standard basis to the generators in the P. So we have a surjective map like this. This is the reason why any module, I don't use that P is projective at the moment. This is true for any module. I can take any module, choose a set of generators, and I get a surjective map like this. So this is the reason why any module is a quotient of a free module. But of course, I could have a kernel.
P can be not finite. Yeah.
Not necessarily, no. So let's call this map pi. Then I can say that the module k is exactly the kernel of pi, right? And this is the kind of the usual reason how you can usual construction how you can get a short exact sequence. You start with a surjective map, compute the kernel, and you can always complete your surjective map to the short exact sequence by adding the kernel. It always works for any surjective map. Okay, so k is the kernel, and now by the condition 2, here we assume that 2 is true, so we know that any such short exact sequence we have p on the right actually splits. So then k direct sum with P is isomorphic to the middle term free module on the set S. So we finished the proof from 2 to 3. So any projective module is direct summand of a free module. Now 3 to 4. 3 to 4. This is probably the only non-trivial implication here. So in the 3, I assume that I continue to assume that I have this isomorphism because I need this notation, this set S.
Does it imply that any projective module does not have torsion yet?
We will discuss torsion later. Yeah. Okay, so let me assume that I have this isomorphism just to fix this notation for the set S. I need this S in the proof. So we have this short exact sequence in the condition 4. So take a copy of the short exact sequence. So this is the only non-trivial proof in this proposition, how to go from 3 to 4. So take a copy of the short exact sequence for all little s in the capital S. And then we can take the product. So let's take a product of short exact sequences. So we know that if you take a product of short exact sequences, we get a short exact sequence. Okay. Now,
And what is this? S is like a generator, so.
yeah, so we fix this in the beginning of the proof. So the set S is given to us, and we take a product over this set of as many. We take as many copies of this given short exact sequence as we have generators in the free module on the right. Okay, so then the next observation is that instead of all these products, by the universal property of the sum, I can write that this is the same thing as the hom R to the S M prime. So that was a property. I guess I left this as an exercise, but the proof is the same as the dual property for the products. So that's something that we discussed last time. Instead of products, I can replace all these three terms by the homs. Now still will be an exact sequence of the homs. Now next step is to replace this free module. Well, by the way, is this clear why I can do this? If you try to compute, remember that if you try to compute hom between the direct sum of modules and some module, this is isomorphic to the product, where you have product and then you compute homs between the modules. But homs between modules, it will be just a ring and a module, and hom between ring and the module is just a module. So here I'm using kind of trivial observation that the hom between R and M is always isomorphic to M. Do I need to write this more explicitly? Is this?
When did we usually product? We said that product is just this.
No, this is a free module on the generating set S. So we have as many elements here as we have here. Oh, maybe, okay, so first isomorphism. Product like this is the same thing as a product like this by the first line. And then we know already this is isomorphic to the hom. Well, here I need to write something like this. But this is by definition this object. So this is what is hidden in this isomorphism. And how to show that this is true?
Well, you take any element of the module and it induces a homomorphism from R to module, which sends any scalar to the scalar multiplied by the chosen element.
Yeah, so to define a homomorphism from a free module, and in this case it's just a free module on one generator, it's enough to understand where this generator is mapped. So such homs are exactly the same things as well. You need to understand where, okay, so this is a map from F R to the M, but this is completely determined by the image of the element 1. Because if you know where 1 is mapped, you know where every element is mapped, because it's just an R linear map. And this is exactly the set of all elements in the M. So this is this gives you bijection of sets, but of course you can check that this construction is actually an isomorphism of modules. Okay, so next step is to use our assumption that K plus P is this free module, and just plug in this formula into this home. So, and also, okay, maybe I just pretend that I continue the computation, and I'll get the following. I'll get 0 home K plus P, M prime home K plus P, M home K plus P, M double prime 0. This is the same sequence of homes, since we know that this is isomorphic modules. But again, by the universal property for the direct sums, this is the same thing as the home K M prime plus home P M prime. And you do this isomorphism for all three modules. Okay, I guess I need to write this. So this will be the second term.
But essentially, if the whole sum and the module is equal to product of these of the homes, but since it is finite case, they are equal. It is equal to sum.
Yes.
Okay.
So you said one of the proofs. You know that if you have any sum here, you need to write the product. But for finite sets, the products and direct sums are the same thing. So you get this, or you can just check this directly for two elements. This is also a quite elementary observation. Yeah. So this is the second thing, and the third thing. So this. Okay. Okay, just continue here. So then I'll get the home K M double prime direct sum with the home P M double prime, and this is 0. Now this is a sum of two short exact sequences. So at least we know that the short exact sequence will have home P M home no, not M prime, P M, and then finally home P M double prime is exact. Well, this thing is a sum of two short exact sequences. If this is exact, then each of these short exact sequences has to be exact. Because if you have some cohomology here, it will give you the same cohomology for in the direct sum. So you have two exact sequences when a first argument is k and the first argument is p. So.
How do you derive this last one?
Could you explain it a little bit more?
Well, I want to leave this an exercise. Suppose you have two exact sequences. No. Suppose you have two sequences.
You could copy the argument about homologies.
I'm just going to give you a general situation. So. So are short exact sequences if and only if the following is the short exact sequence.
Exercise.
But this is very easy exercise. Suppose you want to compute some homology for the direct sum. So this is direct sum of the modules, and notice it's also direct sum of the maps. So if you, let's formulate this as a general exercise. You have one complex and you have another complex. You take the sum. Well, I guess it's not very hard to convince yourself that this is actually the sum. This is bullet.
So we still need to understand that the maps between components of between the modules act complement-wise, and therefore it works, yeah?
Yeah, so this is just we can think of it in terms of matrices if you want. You can think that you have two components, and this will be 2 by 2 matrices where you have maps on the diagonals and zeros outside of the diagonal. And then what you just need to understand is how to compute the kernel and the image of the sum of two maps. And clearly for the kernels and for the image, this is satisfied. And then there is a little exercise about isomorphism theorems to show that this will be true for the cohomology. So from this general observation, it immediately follows that these two conditions are equivalent. But I guess we've proved what we want, right? So if you, unfortunately I erased the statement, but if you go back to the statement, we wanted to show that, yeah, so exactly this statement, that this is exact for any short exact sequence and any projective module P. So this finishes the proof, I guess 3 to 4. If you go back to the 4 to 5, so let me finish the proof like this. 4 to 5 is clear, and 5 to 1 is also clear. So in fact, the last two implications are completely tautological, because if you just go back to the statements, in the 5, you just kind of keep the information which is in the right half of the exact sequence. So 4 to 5 falls immediately, because 5 just contains partial information from 4. And no new information at all. And the statement
5 to 1 is clear.
5 to 1 is clear because this is again just a restatement of the lifting property. It says that you have a surjective map. You take a map from projective map to the one of the maps, then you can kind of lift. So 5 and 1 are clearly just the same properties. Okay. And the last statement about the projective modules. This is also sometimes called the lemma, and this is the Chanuel's lemma. So here we assume that they have two short exact sequences. Let 0, K1, P1, M with the maps alpha 1 and beta 1, and 0, K2, alpha 2, P2, beta 2, M be short exact sequences with modules P1 and P2 projective. So then K1 plus P2 is isomorphic as a module to K2 plus P1. Okay, the proof is not very hard, I would say quite pleasing. We just define module N as a submodule in the direct sum of P1 and P2. So this is by definition all ordered pairs X and Y in the P1 plus P2, such that if you apply beta, so you need to apply beta 1 to the X and get the same result as the beta 2 applied to the Y. So this is some submodule. It's not very hard to check that this is actually a submodule in the direct sum of P1 and P2. So let phi from this new module n to the P1 be the projection right? From the direct sum, you have two projections to P1 and P2. You can compose this with the embedding of the module n into the direct sum and get the projection from the n to the P1. So the kernel of this projection phi, well, this is pairs x and y in the direct sum, P1 plus P2, such that, well, x is equal to 0 and the beta 2 of y is equal to 0. Right, so we're trying to compute the kernel when you project on the first argument, so it means that you want to consider elements where x is equal to 0. But now if you look at this condition, for again x equal to 0 here, you get beta 2 of y is equal to 0. This is beta 2. Well, if the first argument is fixed and just equal to 0, so this module, kernel of phi, is isomorphic all the y's such that the beta 2 applied to y is 0. So this is exactly the same thing as the yes, yeah, this is exactly the kernel of beta 2, but we can do even better if you look at the beta 2 here. So what's the kernel of beta 2? This is K2. So we get a short exact sequence. K2, N, and P1. Now, I guess the only thing that we haven't discussed here is that if you consider this projection from the N to the P1, then this map is clearly surjective. But I can do the second projection. I can do projection from N to the P2 and I get exactly, well, first of all, this splits, of course, because P1 is projective. So this is P1 plus K2. But for the second projection, I'll get exactly the same thing. I'll get now K1, N, and P2. The proof will be exactly the same. And this follows that N is also isomorphic to the K1 plus P2. Okay. This is all I want to say about projective modules. Let's go to the next chapter. Chapter 3, tensor products. So first section, 3.1, definition of tensor products of modules. So I hope that you still remember what the tensor product of modules is, so I'll just briefly repeat the construction. So here we have two modules, M and N are modules. Definition. So I'm going to give you a constructive definition of a tensor product. So first of all, we define two modules. So the module T is by definition the module spanned by the finite sums so finite sums where you take elements in the Cartesian product of the M and N. So here all xi's are in the ring, mi is in the module M, and I are in the module N. So this is module T. Now you can define submodule of this T, T0. So this is a submodule spanned by the following elements. So there will be 3 types of elements, maybe even 4 types of elements. Okay. So in the module G, you consider all the finite sums of this form, where you have some coefficients from the ring, and elements are in Cartesian product of the M and N. And then you consider submodule T0, where you consider what can be generated by all the elements of this form. So
M is the element of M.
M, yes, thank you. So M is an M, N is an M. You take all the possible elements from these modules, you take all the possible x in the ring, and you form all these kind of elements of the 4 types. And you span a module by these elements. So then the tensor product, by definition, M notation for the tensor product is this. Well, I don't know. You're supposed to read this as a tensor product of the M and N over the ring R. This is by definition the quotient of the T by the submodule T0. So this is a constructive definition of a tensor product of 2 modules. Well, why this is an interesting definition? Well, because if you look at the canonical projection, so the canonical map from the Cartesian product to the tensor product, and this map just takes pair M and N and sends this to the tensor product of the 2 elements. More or less, this is a definition of the tensor product of 2 elements. You take this element, right? So this lives in the T0, and well, you can as well say that this is by definition the Mn plus T0, this class. Okay, so we have this canonical map, and this canonical map has the property that this is bilinear. So pi is bilinear, which means the following. So let me just give a general definition. A map between Cartesian product of 2 modules to some other module, L, is bilinear. Oh, you know this from linear algebra. So let's call this map maybe B. So if B M N N and N prime is the same as the B M N plus B M N prime. Right, so if you fix the first argument, this is linear in the second argument. I also need to add mxn, the same thing as x b mn, and of course this has to be true for any m in the m and n prime in the n, and this is for any x in the ring R. So what I have here is just the condition that this map is linear in the second argument when the first argument is fixed, and of course I have the same 2 conditions for the first argument. If I apply b to the m plus m prime with a fixed argument n, this is the b over the m n plus b will be m prime n, and finally b x m n is x b. That's a general definition of a bilinear map. This of course works for over any commutative ring for any three modules m, n, and l. And this map that we constructed is bilinear. Well, that is essentially follows immediately from the definition of T0, because in the T0 we put exactly those elements that we want to punish for bilinear maps. Okay, so this is a bilinear map, and pi is the universal bilinear map. This means the following. If now f so if f is any bilinear map, then you can do the following. You take this m product with n, you have a bilinear map f, then you have also a canonical map pi to the tensor product, which you always have. And then so f prime is linear. So then you can do the following. So f is a given bilinear map. So pi is a canonical bilinear map that we always have. I claim that for any map f, there is a map f prime that, so, well, this map f prime is a linear map, and also this triangle is commutative, meaning that if I apply pi, then I compose this with the linear map. Notice that the composition of a bilinear map and the linear map is a bilinear map, and this is equal to the map f. So this is the universal property of the tensor product. So today I'm out of time, so we continue with the tensor product next time.